Next up, I'm delighted to introduce a Nobel Prize winner who's deigned to join us. Sir Konstantin Novoselov was a Nobel laureate in physics in 2010 and is going to share an insight on the intersection of advanced materials and quantum technologies. So, welcome.
Thank you. Afternoon. Really great pleasure to be here. Dmitry, thank you so much for this invitation. So we know each other for some time. Thanks a lot for setting up my talk. I didn't exactly know how to put myself. I'm a different kind of quantum, more topological person, playing a lot with new materials, topological materials, and so on. But let me give you just first a little bit different perspective of why do we need new type of computing. And let me start with this famous book of Francis Fukuyama, the End of History. So of course, the book is 1992. Probably at that time you could really talk about the end of history. It's a bit laughable from the modern perspective, and if you ask me, I would much prefer to be stuck in 92 rather than in the current climate, but much less gray hair and so on. But in terms of technology, so it was of course meant about on the stability and the division of the world. But on the technology side, it was exactly the same. 92, you would feel that everything is already discovered. So the Moore's law gives you stable but gradual progression of our technology, and then the new millennia came, and it's like a renaissance of science. There is topological materials, and there are human genome sequencing. There is CRISPR-9. There is gravitational waves discovered, quantum supremacy demonstrated or not. Now generative AI as well. So it looks like we're living now in a renaissance of technology, but of course any innovations, they would usually come at a cost, and so we simultaneously with this technological revolution, we had to learn new words like sustainability, like Kyoto Protocol, and so on. So of course, once there is a problem, we start to search for a solution. People talk a lot about the sustainable technology. There are multiple sustainable solutions there, but all of them at the same time, they also come at a cost, and there is like a whack-a-mole effect. So you produce a solution, but then it creates a problem at the same time as well. So what I would like to say that it's not enough these days to simply produce a sustainable circular economy. We really need what I call a spiral economy, and just let me just try to explain you what we do. What do I mean by this? So already now we are so bad in our CO2 emission that we had to actively extract CO2 from the atmosphere. So there are plants being built everywhere. There are those plants in the Emirates. There are plants in Singapore as well. A bit of a useless, honestly, but we were still there. So but we still have to spend energy, hopefully renewable, to extract CO2. And then what we do, we just bury CO2 somehow underground, underwater. So for it, we just need to take it out from the atmosphere. But now think if we can actually use it somehow, if we find a way to reduce CO2 at the same time as we extract it and turn it into some new advanced materials. So we've been working recently a lot with graphene, carbon nanotubes, some other forms of carbon, and then if you can use it, so it would be already better than burying it into, underground. The problem is that we have to extract trillions of tons of CO2. Who would need trillions of tons of graphene or carbon nanotubes? Computers, so quantum computers, even those topological ones, you would need micrograms. Even if you replace all the touch panels on all your mobile phones, you would need a kilogram of advanced carbon materials per year, just because it's so thin and so light. Luckily, there are technologies which can utilize that amount of advanced carbon, for example, advanced concrete. So adding minute amount of graphene or carbon nanotubes into concrete increases the compressive strength of these materials by 30–50%. And of course, concrete industry is one of the largest CO2 emitter by itself. So by extracting CO2 from the atmosphere, turning it into advanced carbon, putting it inside concrete, we reduce the CO2 emission even further, and that's what we call spiral solution. And so if we didn't have enough of the old technologies mentioned today, so there is another one, blockchain. So you can actually you can register it on the ledger and apply for the carbon credit. So, there is another source so these days we're actively doing it together with many petrochemical companies. I'm sure you've seen those flares everywhere in the world on the petrochemical plants, on the refineries. And there we've got everything what we need to produce advanced carbon materials. We've got the high temperature, the carbon source, so we can turn it into advanced carbon really easily. Now, just coming to the future of the computing, and for years, the sustainability of our computing has been guaranteed by two laws, by Moore's law and by Denner's law. So Moore's law tells you that you double the number of transistors per chip every 1.5 years, and Denner's law tells you that even though you double the number of transistors, you don't increase the energy consumption, because those transistors become smaller and they consume less energy. So together, these two laws guaranteed sustainability of our computing industry. Recently, it has been broken, and overheating is so we just face this power wall these days, and overheating became a problem, and our computers now consume about 4 to 5% of all the energy produced. With the advent of AI, it's prognosed to be above 10%. Within the next 4 years, so it's really a huge amount. We have to build nuclear power stations basically next to our data centers if we want for them to work without any interruption. Simply grids are not, and I've seen stories even from the commercial world that people in the finance trading, they're not allowed to build data centers simply because the grid cannot carry this capacity. So we really have to do something very, very, very urgently. Luckily, there are solutions. So quantum is definitely one of those. Neuromorphic computing is another one. What was already introduced in the previous talk, probabilistic computing, and that's exactly where we're sitting. So we're designing and developing the hardware for the probabilistic computing. So now at this moment of time, we have a very interesting situation. We have the fast developing of the quantum computing, but at the same time, the fast developing of AI. And we already heard from Lyria's talk that AI helps to design our quantum computers. The question is, who is going to help the AI? Because all the large language models, we're talking about foundational models, and every single field is talking about foundational models now. Material science, chemistry, fintech, they all talk about the foundational models. It's going to cost us enormous amount of energy unless we do something radically different with our chips. So as I said already, it's about. So I don't think. So realistically, we will have a solution from anywhere within the decade, and the energy consumption is going to grow above 10%, probably even around 15% within the next 10 years. So and here the probabilistic machines can actually enter into the picture, and they can definitely create the solution for the energy for energy saving, but at the same time produce faster computation within a very short period of time. So all the algorithms are there. In principle, quantum algorithms can be, so it's been mathematically demonstrated that quantum algorithms can be projected on the probabilistic machines, but realistically you don't really need that. It's the different type of the tasks which you're going to solve with those machines, and there are a number of different physical platforms which are available right now. So in terms of the scalability, because there is no problem of the coherence, already now there are orders of magnitude, like 4 orders of magnitude more probabilistic chip bits per chip available. In terms of the energy, is enormous amount of saving. I will probably explain you later why is it so. And so we need to. So when people talking about the speed and how much faster, it really depends a lot on the task and all on the algorithm. So I won't pay too much attention to that. So it's one number for one particular algorithm. So we really need to discuss task by task and algorithm by algorithms. So just to introduce what is probabilistic computing. In the standard computers, your information is stored in terms of the zeros and ones, and those are deterministic. In the quantum computers, you've got an entangled state between 1 and 0, so you're living on the block sphere. And the probabilistic computer, what it basically can offer, its major characteristics that it can give you a random number with a given distribution, so a weighted random number. You would ask, okay, who cares? There are lots of random numbers in the world. In fact, the generation of the random number in the modern computer, which takes quite a lot, especially for the regression, for the back propagation, for the AI tasks. So it's a lot of random numbers needs to be generated, and to compute a weighted random number is a huge mathematical task. And basically what we do, we just try a physical system which is capable of doing it as a chip physically, rather than computing it inside your computer. Funny enough, it actually has to be done in a quantum manner as well, because of course there are lots of random processes in this world, like fluctuations of the density of gas in this room. Any resistors give you Johnson noise. The problem is that you really need quantum noise because that would amplify you and give you energy advantage. If the classical noise, you would still have to amplify it, and then thermodynamics won't allow you to get any energy advantage. So it has to be quantum process. So that's why it's either superconductors being used for the probabilistic machines, or it's the magnetic tunnel junction, basically spin or quantization fluctuation. But it has to be quantum process there to gain some energy. So I won't go. So probabilistic computers there already, but they're usually realized on FPGA, field programmable gate arrays. They give you speed advantage in certain tasks. The problem is they don't give you energy advantage. If we're serious for our sustainability goals and if we're serious to make our data centers sustainable, we have to find those physical representations of the p-bits, and that's exactly what we're doing in our labs and in our companies. So one of the example is based on the one-dimensional superconductors, and then and it's the beauty that it's controllable and it gives you a weighted random number. So we basically inquire it many times. Ultimately, we can inquire 1,000 times every nanosecond. It depends on how fast your readout is, and depending on the external parameters, it would always give you 1, it will always give you 0, or it can give you any random number in between. And because it is controllable, it's easy to be connected between each other, and then you can basically build it into a net. So what kind of problems it can solve? So in principle, you can use it to do the usual LLMs, but that's not where the current algorithms are. It's doable, but it would require change of many algorithms, which is probably not feasible simply practically for the next few years. So typically it is optimization, it is Boltzmann annealing, it works similar to the quantum annealing for the quantum computers, but it's very easy then to map on a number of different applications. For example, image generation. So even with a very limited, so we use standard cryostats, so very limited number of p-bits. So you would generate a decent image. Portfolio optimization is a standard problem. On the paper, we are extremely rich, so we optimized our portfolio by 1,000% return. Unfortunately, it's on the past data, not on the future data, but okay. And so it was already mentioned in the previous talk, the travel salesman problem is another very beautiful example of optimization, and I'm sure that Abu Dhabi ports would benefit from it. So the data in Abu Dhabi port is, of course, extremely complex because it's the logistics of the ship, it's logistics of people, of containers, of goods. So it's quite a lot of we looked into it. It's quite a lot of new mathematics which needs to be done here, but it is doable, and I'm sure that with the probabilistic computers it can be done. So just to finish, to say that it has been projected. It's not our data. It's from other people. So in terms of the flips per nanosecond, and in terms of the energy consumption, the use of the physical p-bits in combination with FPGA and standard CPU can bring you orders of magnitude speed and what is more important, probably energy advantage. And I'm sure that in the next few years, at least maybe 20 years, that's our way forward, how to make our computations sustainable. So I will just leave this case, this slide for you. So the kind of use cases which you can do. It's as I mentioned already, image generation, logistic optimization, portfolio optimization, drug discovery. So because it is the standard annealing processes. So that's quite a few algorithms already exist, and its realization it's reasonably simple because it doesn't need entanglement. So you can actually do it on a very simple cryostat. So it works much more reliably in that sense. Thank you so much. Thank you.